Okay, here are the continuation of the notes for section 2.3. And we're still in process of learning derivative rules. Okay, I'm going to discuss the notes for the second part of 2.3 shortly, but let's talk about a couple other topics that we have been examining, that we've been working with before I go back to 2.3, looking at some more derivative rules. I want to discuss for just a minute what this means. And I want to ask you to sketch two different graphs who has a limit coming toward 3 that exists on the graph, and the limit is 4. Take a minute and sketch two diagrams on your paper where it describes this situation. So, I want to ask you, what if I had something that looks like this nice curve comes up? So what do you notice about this curve? It's continuous. The limit coming from the left and the right both equal 4. And the value of f of 3 equals 4. So it's continuous at that point, and the limit's equal on both sides, so the limit exists, and it makes a nice little graph. But what if I had this? Let's look at this situation. Is the limit coming from the left and the right both 4? And the limit coming from the right equal 4? So does the limit exist? Yes, because the left hand and right hand limits are equal. So the limit as x approaches 3 of f of x equals 4. But let me ask you this. This graph is continuous. It's differentiable everywhere. I can draw a tangent line at each point. Is this graph continuous? It fails the conditions for continuity at a point. It's discontinuous there. F of 3 is undefined. Therefore, can I sketch a point of tangency there? Think about that condition. So if a function is discontinuous, is it differentiable at a point of discontinuity? All right, think about that question. We're going to talk about it tomorrow during class. All right. Now then, before we get to we're going to, on this set of notes, we have several topics that we're going to talk about where we need to bring some threads together. We're going to talk about where functions are differentiable. Second topic we need to talk about is derivative notation. And how to use it. Third thing is we've got some really complicated looking derivatives coming in our homework. We need to discuss our algebra. Then we're going to go back to section 2.3 to more derivative rules. And in those derivative rules, we have more trig derivatives. And we have higher order derivatives. So I'm going to cover these 4 things in these notes. And I'm going to give you examples as we move along. So let's talk about where functions are differentiable first. Well, we have 2 types of functions that we're going to be working with. Continuous and some that have some discontinuity. This one I'm going to ask you about tomorrow because we just discussed those conditions. So we're going to talk about that tomorrow during class. But continuous, they are differentiable everywhere but you got 3 conditions. Talk about those 3 conditions and we'll talk about it at the beginning of class and why they're not differentiable there. All right, so whether a function's continuous or not is a big topic about taking the derivative. We've got to talk about where they're differentiable and why it makes it true. All right, let's talk a little bit about derivative notation. We know that if we're given f of x to indicate that we've taken the derivative, we can write as f prime. If we're given y to indicate we're taking the derivative, we write y prime. We know that as uppercase F, we do an f prime. And then there's some other notation. But I don't know if you've noticed in the book, it also has this notation that means derivative. And this notation means the derivative of y with respect to x. That means you took the derivative of y equals equation, and on the other side of the equals mark were x's. All the variables in your y equation were x's. And we know that may change according to the type of equation that you have. So for example, if I have y equals 3x squared minus 4x plus 2, and let's say I want to use this particular notation, technically we should be putting d dx in front of that term. And if you do one thing to one side, you have to do it to the other. The d dx tells you that I'm getting ready to take the derivative. So if I'm going to take the derivative of this term, that's the derivative of y with respect to x. But we most times write it as y prime. But these two things mean the same thing. But it's going to mean a lot when we start changing the names of the equations. Then we can take the derivative of each of these terms, which we know we can do individually. So this is 6x minus 4. If we had the area of a square is s squared, and I want to know the rate of change of area, with respect to the length of the sides, then I would write, all right, I want to find the rate of change with respect to the length of the sides of area. I'm going to take the derivative with respect to the length of the sides. So the rate of change of area with respect to the sides is equal to 2s. Sometimes we change up the notation according to what the problem asks for. You will see a lot of discussion from here forward. We might do d dx cosine x, and that tells you, the reader, we're taking the derivative of cosine x with respect to x. is equal to negative sine of x. So there's a lot of little things that we're taking shortcuts on recently that are going to start coming in a little bit more, presence in our homework. Okay, let's talk a little bit about algebra. Now that our derivatives are getting a little more complicated, we're going to have to simplify them before we can do certain things with them. So let's say that we had a derivative that looks kind of like this. I've taken the derivative, I have applied my quotient rule, or whatever rule I've used, and this comes up to be my derivative. You're going to need to simplify this expression. That's the exponent of negative 1/3. To simplify this expression, you look for common terms. So happens there are two sets of common terms in this expression. I'm going to factor out each common term. All right, so my first common term is the base of x. And my second common term is the base of x minus 1. If you remember from pre-cal, you're going to factor out the lowest exponent. So here we go. I'm going to factor out my lowest exponent. So my base is x. I have to compare 2/3 and negative 1/3. Negative 1/3 is my lowest exponent. My next common term is x minus 1. So I'm going to take out an x minus 1. But my lowest exponent is 1. Now I have to subtract exponents. So 2/3 minus negative 1/3 leaves me with x to 3/3, which is just plain old x. X squared minus x minus 1 to the first is just x minus 1. Right, next term, don't forget your operation sign in the middle, minus, and then 3. I factored this term out, and I factored that term out, so I'm finished with the numerator. And yay, it made a little bit more simpler expression for me. I notice I have x minus 1 to the first and x minus 1 squared, so I'm going to go ahead and bring this down the denominator. I'm going to go ahead and distribute here. That's x squared minus x minus 3 over x minus 1 to the first. So on the homework that you will be checking for 2-3 that I've already posted for you, I have gone ahead and simplified some of the expressions. But we're going to work in simplifying our algebra. And I'm going to give some examples, some hard ones, where you're going to need to practice factoring in order to continue work with the derivative. Okay, next is our derivatives. So I'm coming back to 2.3, more derivative rules. And we're going to, more trig rules. And I'm going to use our new derivative notation that I just talked about. So I'm going to take the derivative of tangent x. So this lets you know, you the reader, that I'm taking the derivative of this function with respect to x. The derivative of tangent x is secant squared x. The derivative of respect to x of cotangent x is negative cosecant squared x. These are easy derivations, but it's easier for just to memorize them. The derivative with respect to x of secant x is secant x tangent x. So I hope you heard me say you need to memorize these. The derivative with respect to x of cosecant x is equal to negative cosecant x cotangent x. So these are going to be included in the homework that you need to work in class on Friday. So there's some extra derivative rules. The next topic in 2.3 that we need to talk about is higher order derivatives. And this is on page 125 of your book, if you want to look at that page. So to express derivatives, higher order derivatives, all the notation is written for you on page 125. I'll show that to you. This is first derivative. Second derivative uses two little hash marks. Third derivative, fourth derivative, fifth derivative, they'll just use a superscript to describe which derivative. F prime is first derivative, F double prime is second derivative. Notice the second derivative notation for when you're dy dx. Second derivative of y with respect to x, it's not an x squared, it just means you took the derivative a second time. And so we're going to work more with these notations and how to, especially with this notation, and how to write it appropriately. But let's look at an example. Let's say that I had y equals, and just for sake of time, let's do a basic one. 3x to the fourth minus 2x cubed plus 4x squared minus 5. Let's just do a basic example. Okay, let's find the first four derivatives. All right, so the first derivative is 12x cubed minus 6x squared plus 8x. The second derivative is 36x squared minus 12x plus 8. The third derivative, is 72x minus 12. And the fourth derivative, you can put four little marks up there or just put a superscript of 4, would be 72. So when you're finding extra derivatives, it just means keep taking the derivative. All right, let's discuss some of this tomorrow in class.